Hi, and welcome back to Codex. Our talks this summer feature graduate students and postdocs who are nominated to speak by their senior colleagues. Today, we have Paulina Hoyos from the University of Texas, who will tell us about manifold learning and the presence of symmetries. Take it away, Paulina.
Thank you. I'd like to thank the organizers for this summer series, and special thanks to Emily, who helped me turn a rather technical talk into this great talk that you're all going to see. So I'm going to talk about this project that I've been working on with my advisor, Joe Kilio, here at UT Austin. Um, uh, so we want to understand the structure beneath a finite data set. So be it, for example, data coming from simulations, PDEs, or here we have images from cryo-EM, where you freeze a molecule and basically take a picture of it, which is what we are seeing here. So this is the molecule, and these are the corresponding 2D images that you get from those pictures. And we want to do two things. We would like to understand what's the hidden lower dimensional structure in this data, and we also want to extract key features from the data so like we can understand better what's going on. Okay, so first of all, we want to work with nonlinear methods because sometimes linear projections are just not enough. For example, here in this helix, like if we project either to a one-dimensional subspace or a two-dimensional subspace, we're losing structure in the data, and that's not good. We don't want that. Second, we also want to include group symmetries because they allow us to understand better what are the key features in data. So if we understand that this data has a 2D rotational symmetry, then we're gonna know that we only need two parameters to fit this data instead of three, so that might give us better results. So in this talk, I'm going to talk about graph Laplacian methods in manifold learning, which give us nonlinear methods for understanding data. I am going to talk about symmetries in data and why we care about that, and then how we can combine these two into the work that we did, which is about the group invariant graph Laplacian. And I'm going to go to explain what we did. So let us start with graph Laplacian methods in manifold learning. So the basic idea is that we're assuming that data lies on a lower dimensional manifold that's embedded in some higher dimensional Euclidean space. And we do not know explicitly what this manifold is, but we would like to see if we can say something about this manifold or about the data that lies on this manifold. And the idea is that we're going to do this by approximating the manifold by constructing a graph from the data points. So if we start here with some random scattered points and we start connecting the dots, we see that this starts to resemble a circle or maybe just like an annulus. So we hope that the structure of this graph is going to correspond to the geometric structure of the manifold that our data is coming from. Okay, and we're interested in graph Laplacian methods because from graphs we can obtain matrices, and once we have matrices, we can apply all of our well-known linear algebra techniques, which is great. So here we have an example of a graph, and out of it we can construct the adjacency matrix, which tells us what are the different connections between the vertices of the graph. Okay, so how are we going to construct this graph from data? So we're going to take this weighted graph where the vertices are the data points themselves, and it's a complete graph where we're going to give a weight between each pair of edges as given by some chosen affinity kernel. The common choices are just like the Gaussian kernel, 0, 1 kernel, where like you draw a line if the points are close enough or 0 otherwise, or k nearest neighbors kernel. Okay. So once we have constructed our graph, we can define the graph Laplacian. So we start by taking this degree matrix D, which basically counts the number of neighbors of a vertex, but it does it in a weighted way because the edges might have different weights. And then after we have constructed this degree matrix, the graph Laplacian is just D minus W, where W is the weight matrix that's coming from our affinity kernel. So it is easy to see that L is a symmetric matrix because both D and W are symmetric. And moreover, we can show that it is a positive semi-definite matrix. So we have the matrix definition of the graph Laplacian, but we can also give a functional definition where we see that it acts in a function defined on the vertices by this formula. And what this is doing is that we're taking weighted averages of the function at the point and its neighbors. So let's take a look at an example. Here we have a cyclic graph. Yeah, so all of the vertices are connected to its two nearest neighbors. And the weight matrix just looks like this. So you put a 1 wherever you see an edge here. So the graph Laplacian is this matrix that we have here. So just like the minus W, so we see that we have 2's along the diagonal because each vertex has two neighbors. And yeah, we can just immediately see that this is a symmetric matrix. Okay. So this is nice, and like in this case, this graph is it's very nice because each vertex has two neighbors. But it could happen that you have graphs where one of the vertices has too many neighbors, and that can create some imbalances. So we fix this by normalizing the graph Laplacian. So what we do is that we multiply on the left by the inverse. And this is a sensible normalization for the graph Laplacian because we can give a probabilistic interpretation to what's going on. So when we normalize it this way, this matrix, the inverse W, is a row stochastic matrix. So it gives us the transition probabilities for a random walk on our graph. And this is great, but the normalized graph Laplacian is no longer symmetric. However, we can prove that it is similar to a symmetric matrix, and therefore it is diagonalizable with real eigenvalues. So that's important, and that's what we want. So that's really good. And here I have an example where we see here that this vertex seems to be way more connected than the other vertices. For example, here 2 only has one neighbor. And this gives us this graph Laplacian. So when we normalize it, we obtain this other matrix. And here we see that this matrix is no longer symmetric. So this is a simple example of a normalized graph Laplacian. Okay, so why are we interested in looking at the graph Laplacian? Well, first is that it gives us a method to apply our well-known linear algebra techniques. For example, we can do spectral embedding of data. I'm going to briefly explain what this is, but more importantly, it gives us a finite dimensional approximation of the manifold Laplacian. So when we have just like a finite number of data points, we can construct the graph Laplacian, but then we can imagine that we start adding and adding more data points until, like, let's say we have an infinite number of data points, and in that case, we obtain the manifold Laplacian. So this is what I want to focus on. Okay, so let's review the spectral embedding algorithm. The idea is to compute the normalized graph Laplacian from data. Then we compute the k smallest corresponding eigenvectors. And then we're going to use these eigenvectors to embed our data in a dimensional Euclidean space, as given by this formula. And after we do this, then this can be used, for example, for dimensionality reduction or for pre-processing data before applying some more sophisticated methods. And we see that after we've filtered things through the graph Laplacian, now we have just vectors, and we can do the same things we're used to in our data science algorithms or methods. So this is great because we're back to linear algebra, which is what we like. Okay, now let's focus on the manifold Laplacian. It's also called the Laplace-Beltrami operator, and it is defined as the divergence of the gradient. And it is an operator on manifolds that describes heat flows. And well, the solution of the heat equation on a manifold is given by convolution of the initial condition with the Gaussian kernel. So here we start to see the connections between the graph Laplacian, where we use Gaussian kernel, and the Laplace-Beltrami operator. And moreover, the eigenfunctions of this manifold Laplacian form an orthonormal basis for the space of functions on the manifold. Okay, so this is the first like well-known result, and it's that when we have n data points sampled independently and uniformly from the manifold, and we construct the normalized graph Laplacian from the Gaussian kernel, then the normalized graph Laplacian converges pointwise to the manifold Laplacian as we let the number of data points go to infinity, and we decrease the bandwidth parameter in our kernel. So this is the precise formula, and I would like to focus on this last term, which is called the invariance term. And this term is giving us a relation between the number of data points and epsilon, because, for example, epsilon cannot go to 0 too quickly. It has to go to 0 according to how quickly the number of data points is growing. Because if we have too few data points and epsilon is too small, then it's like we're not going to capture enough data points with our kernel, and we don't want that. So this term is very important. It tells us the relation with parameters, and I'm going to come over this variance term later when I state our results. Okay, so this theorem is great, but note that data points have to be sampled uniformly from the manifold. So someone might ask, what happens if we have data points that come from a non-uniform probability distribution? So this could happen with, for example, data coming from PDE simulations. So in that case, our graph Laplacian is going to converge to the Fokker-Planck operator. And this Fokker-Planck operator is just like the natural way to extend the Laplace-Beltrami operator to the case that we have a probability distribution on the manifold. And we do so by adding this first order term that accounts from drift forces in the evolution of our system. So think, for example, about Brownian motion. So for example, how smoke comes out of a chimney, or how pollen moves in the air. So in this case, we have like a diffusion process, but there are also drift forces that are going to influence our system. And so now when we have data that's sampled from a probability distribution on the manifold, the result is basically the same. So we're going to converge pointwise to this Fokker-Planck operator with the same convergence rate. And one might think that this result is like a lot more complicated than the previous one because the Fokker-Planck operator is more complicated, but actually if you prove convergence to the Laplace-Beltrami operator, then these results comes very easily as a corollary. So that is great. That means that we basically have to prove convergence to the Laplace-Beltrami operator. And that is what we're going to do. Okay, so why do we care about these convergence theorems? So, well, first of all, the heuristic argument that we gave before, where we hoped that the structure of the graph corresponds to the geometric structure of the manifold, is now given in a precise mathematical way. It also gives us a way to understand the relation between the number of data points and the bandwidth parameter um, for our kernel, because when you're doing experiments, for example, trying to tune the bandwidth parameter can be quite difficult. So if you have an idea of more or less what this epsilon should be, depending on the number of data points that you have, then that's actually really helpful for experiments. And it also allows us to estimate the error in our approximation. So if we have a data set and we know that there are 10,000 points, for example, and like we don't have a way to obtain more data points, then we're going to have a rough idea of how well we are approximating things. So these convergence theorems are great. Okay. Now let's move on to symmetries in data. And then like it's not a secret that real world data just is full of symmetries. So take, for example, in image classification,
Looks like Dustin's gonna have to do some editing. Hopefully the internet is good enough when she comes back on.
This is good because Dustin's always eager to do all of the post-processing for the codec seminar in a timely manner. So he can edit out me saying this about him.
Think you're just encouraging him to like delay the posting.
Release it uncut. I want this on the record.
Yeah, I think I'm not going to edit it and just keep it on the permanent record of YouTube that I hate you guys.
You'll note the lack of inclusive you guys there. Just pointing that out. Welcome to the New World Order.
I mean, to me, you guys is not gendered, so that means he also hates me. It's okay. I do not have an email from Paulina right now. Maybe something, yeah. There she is. No? Ah, yeah.
Hello. Can you hear
Hi.
me?
Yes.
Yeah, so I am at my office hoping that the UT internet would be good enough, but I don't know what happened. Like, yep, it's down.
It's yeah. Yeah.
Okay.
Dustin's gonna edit all this stuff out in the middle. So
Okay. Okay.
you froze like you had kind of you were showing the pictures with the second round of pictures with the symmetries and data, and that's
Okay.
like the slide you were at when it froze.
Okay.
One with the cats in addition to the um X-ray crystallography data.
Okay. Let me share again.
Yeah, that's what you're at.
Okay, so here.
Yes.
Okay. So I was saying how like the picture of a cat is still the picture of a cat. No matter if we rotate it or if we reflect it or shift it. It's still a cat, and image classification should recognize all of these as a cat. But also, here we have some other images from cryo-EM, where we can see that here is just some rotational symmetry in all of these images from this molecule. And in this other picture, this is the 3D density map of some protein, and this is these are the corresponding 2D images. So, I mean, it's no secret that symmetries appear in real world data. And I think that this is really interesting. And good mathematical models should respect symmetries. So they should be invariant, where no matter what rotation or reflection we do to our data, we still obtain the same result. So in image classification, this should always be classified as a cat. But for example, when we have proteins or similar molecules, if we rotate them, this shouldn't affect how we're going to predict the atomization energy for such molecules. But we also have equivariant models, where doing a transformation of our data results in a transformation of our model or of our prediction. So in image segmentation, if we reflect the image of the cat, then our model should reflect accordingly how it's doing the segmentation. Or if we rotate a molecule, then the different forces should be rotated accordingly. So we have invariant or equivariant models. And we want a mathematical model for symmetries in data. So we're going to do this by considering a compact Lie group that acts freely and isometrically on our manifold. And here we have an example where the manifold is an annulus. And we see that this annulus has a 2D rotational symmetry. So in this case, G is the SO2 symmetry group. So if we have a data point here and we rotate it, then we obtain another valid data point. Yeah. So, for example, in image classification, our group would be SO2. And in cryo-EM, for example, our symmetry group could be SO3. But there are many different examples of how these mathematical models arises in real data. Okay, so how are we going to include these symmetries in our different manifold learning methods? The first idea is just to do data augmentation. So that means that we're going to add a finite number of transformed data points. And this is a very natural idea. So if we have here this cat, where we can just like rotate it by, let's say, 90 degrees, and then, oh, well, our model should learn to identify this as the image of a cat. But this has several problems because if we do this, we're really just getting things that are approximately invariant to the action of G, because we can only add a finite number of data points. And this creates computational challenges because now we are augmenting our data set by a factor of k. So that's more data that we have to deal with. And I think maybe the most delicate problem is that we could introduce correlation in the noise of different data points. And we don't want to introduce these correlations. So we need some kind of solution that fixes these problems of data augmentation. And this is where our work comes in. With the G-invariant graph Laplacian, the basic idea is that we want to include the group action directly in the definition of the graph Laplacian instead of moving it to the data. So everything is going to be confined to our, like, to the mathematics. Okay, so the idea is that in our graph construction, we're going to include entire orbits of data points. So now the vertices are going to be this product space of our data points times the symmetry group. And that means that we have to consider weights accordingly, where we are again going to use just the Gaussian kernel, and we're going to input the distances between all different rotated data points. Which means that now W goes from a matrix to an operator because G and H are now continuous parameters. And if we go back to the annulus example, now our vertices are going to be data points times the group SO2. And for the H weights, we're going to consider rotations by different angles. Okay, so we're transforming the domain of definition of our function. So that means that we need to find an appropriate function space for them. And the idea here is very simple. We're just going to take the product measure on this space where we're adding over the number of data points as we did before with the standard graph Laplacian, but now we're also going to integrate over the group. So in the case of the annulus, we're going to be integrating over all angles from 0 to pi. So once we have this appropriate function space, we can define the G-invariant graph Laplacian. So since we no longer have matrices, we cannot really give the matrix definition for the graph Laplacian, but we can use the functional definition, where we define this G-invariant graph Laplacian by how it acts on functions. And it acts on functions just by taking the average of the function at each given point and like all of its neighbors. So this is basically the same definition as before. All we have done is just add an integral over the group. Okay, so we can prove that this operator is compact, which is a property that we need since now we have a continuous group, and it is also a positive semi-definite operator. Okay, so again, there could be some points that are more connected than others, and we want to even this out. So we need to consider the normalized graph Laplacian, where the definition is the same. We just multiply on the left by this matrix D inverse. So note that in this case, D is a matrix because we are integrating here over G, so now it only depends on the data points. And we can prove that this normalized G-invariant graph Laplacian can be diagonalized with real eigenvalues. And these eigenvalues are very interesting. So the idea is to use Fourier analysis to find the spectral decomposition of the normalized graph Laplacian. And so here the idea is that we use the unitary irreducible representation matrices for our group to consider the Fourier transform of the Wij operator. And the Fourier transform is a great tool because it allows us to go from continuous weights to now discrete weights. And that's great because we're back to something that's finite dimensional. Okay. So we proved that this Ln admits non-negative eigenvalues where the corresponding eigenfunctions are given by this formula. And note that this formula is telling us that the eigenfunctions are the tensor product of the irreducible representation matrix with these eigenvectors of these matrices that we can construct from the Fourier transform of W. So we're just like back again to linear algebra because if we have a fixed group G, the matrices UL are known. So we don't have to worry about this part. All we have to do is to compute the eigenvectors of these matrices. So that's great because we have linear algebra, so we know exactly what to do. We have algorithms, efficient algorithms for doing that. Okay, so as an example, consider again the annulus. So we have the group SO2. It is an abelian group, and which means that all of its representations are one-dimensional, and we know exactly what they are. They're just the exponentials that are parameterized by L, which is an integer. So if we want to compute the eigenfunctions of Ln, in this case, we just have to find the eigenvectors of these matrices that depend on L. So there should be an L here, the superscript. Okay. So I think that this is a really beautiful result where Fourier analysis allows us to simplify things. Okay. Now, let us see what happens when we're trying to approximate the Laplace-Beltrami operator on the manifold. So again, we have n data points that are sampled independently and uniformly from the manifold, and consider the normalized G-invariant graph Laplacian that we just introduced. So if we have a smooth function, we can go from this function to another function f tilde on our product space just by considering how G acts on each data point by this formula. So our result is that this G-invariant graph Laplacian converges pointwise to the Laplace-Beltrami operator as the number of data points goes to infinity and the bandwidth parameter of the Gaussian kernel goes to 0. But what's really interesting here is that we get an improved rate that depends here on the dimension of the group. And this is a great result because that means that if we want to achieve a fixed error in our approximation, we are going to need less data points to do that. And this can come in very helpful, for example, when you just have limited data available to you. So you really want to squeeze out as much as you can from your data. But you know that it has some symmetries. So you can use that to obtain better results, which is what we wanted to do. So it is really just like kind of extracting all of the key features from your data that you can learn from symmetries. And I want to say just a couple of words of how the proof goes. All of these proofs are standard and they are divided into 2 steps. First, you take the limit as the number of data points goes to infinity, and you get that graph Laplacian converges to the manifold Laplacian. And this gives us the first error term. But now you also want to estimate what's the probability that the graph Laplacian is deviating from the manifold Laplacian. And to estimate this probability, it basically just reduces to integrating over the manifold. But we know that our manifold is G-invariant. And that means that locally it looks like a product of the quotient space times the group. And we can basically just do some math and reduce the problem of integrating over the manifold to integrating over the quotient. And so that's how we get here. It's D minus the dimension of the group, because this is the dimension of the quotient. So maybe I just want to recall that D is the intrinsic dimension of the manifold that we're working with. Okay. So that's our result. So now let us illustrate it with a basic numerical experiment about the convergence rate. So we're going to let our manifold be the 4-dimensional sphere. So that's S4. And we're going to embed it in C3 via this map, where you just take pairs of points and then just send some of those points to the imaginary components of C3. And then we're going to let SU2 act on the 4-dimensional sphere just by rotating the first 4 coordinates in complex space, and we're going to leave the 5th coordinate of S4 fixed. So this is how SU2 acts on S4. Okay. So for our experiment, we sample 5,000 points from S4. And since this is a pointwise convergence, we need a test function. So our test function is just going to be, you add up the first 2 coordinates of S4 here, x1 plus x2. And moreover, we need to test this at a particular point. So we simply choose this convenient point. Okay, so here we see in red we have the standard graph Laplacian, and in blue we have our G-invariant graph Laplacian, where we are plotting the error against the bandwidth parameter epsilon. So we can see here, the first thing that we can notice is that for the same number of data points, we're able to achieve a smaller error by using the G-invariant graph Laplacian. But it's not only that, it also shows us that like with the same number of data points, you're kind of like your epsilon can be smaller, so that means that you're looking closer into the geometry of the manifold. So you're getting closer to the actual local geometry of the manifold and not looking so much at the ambient Euclidean space. And yes. Okay. So this is great. We can see in experiments how our result indeed can give us smaller errors, which reflects the improved sample complexity that I was talking about. But we also need to address the computational costs of this method. So to find the eigendecomposition of the G-invariant graph Laplacian, which is what we are then going to use to do spectral embedding, we need eigenvalues and eigenvectors to do spectral embedding. We need to compute these weights. And this can be non-trivial because computing here this transformation of how G acts on Xj can be costly depending on the group and the data set that you're working with. So we need a fast algorithm to compute these weights. And we also need a way to do a fast Fourier transform to evaluate the Fourier transform of the weights for our graph. So, for example, there are fast Fourier transform algorithms for SO2, SO3, SU2, but there might be some other symmetry groups that we don't know how to do a fast Fourier transform. So this is something that we need to consider. And well, after we've done this FFT, we need to return the eigenvalues and eigenvectors of these matrices that are just like increasing in size. So that can also be costly depending on how well you want to do, you want to compute the eigendecomposition. So just as an example, let us see here what happens for SU2. So yeah, in this case, the total computational cost is of the order of NQ, where remember N is the number of data points. And on D square, where D is the Euclidean dimension of our data points. Okay, and K here is the is where we are going to truncate our fast Fourier transform. So it's how we're going to truncate this L. Okay. So depending on like what examples you're working with, this computational cost could be something that you want to worry about. Okay. Let me conclude with a summary and some future directions. In this talk, I hope I convinced you that graph Laplacians are a great way to obtain linear methods to study inherently non-linear data. And we also need to take into account group symmetries because they should allow us to understand data better. And if this is a resource that's available to us, we should use it. Just trying to do the naive thing, so direct data augmentation gives poor results. But we've shown that the G-invariant graph Laplacian, it incorporates the group action directly in its definition, so leaving the data alone. And by doing this, we obtain a convergence to the Laplace-Beltrami operator with an improved sample complexity, which means that we need less data points to achieve a good approximation error. Okay. And for future directions, we need to consider ways to make our group invariant methods computationally efficient so that they can be used on scale. Like in particular, this means that we need to use fast Fourier transform algorithms to expand things in terms of special functions. And I gave a lot of examples about cryo-EM. So it would be really nice to demonstrate how the efficiency of our methods on this scientific application. Well, thanks for your attention, and here's the archive number of our paper.
All right, let's thank the speaker by smashing a reaction button.